Antimatter is a concept you've probably heard of. Essentially, it is identical to regular matter particles, from their properties to their ability to form atoms and molecules. The only key difference is that they carry the opposite electric charge. Wave Devil. The electron has a mass of approximately 9.11 times 10 to the minus 31 kilograms, a quantum spin of 1/2, and an electric charge of 1.6 times 10 to the minus 19 coulombs. Here, the coulomb, symbolized as C, is the unit used to measure electric charge. Antimatter version. Antiparticle sibling. Everything went smoothly, perfectly, and without a hitch, except for one minor detail, which was part of a much larger problem. Based on theoretical foundations and empirical observations, we can see that matter and antimatter particles not only always coexist, but also exhibit a perfect symmetry between them. Each particle of ordinary matter produced in reactions appears alongside its corresponding antiparticle. There is only one conclusion. Our universe exists with antimatter particles, and they are evenly distributed in portions alongside ordinary matter. All planets, stars, and galaxies are composed of antimatter, or at the very least, a significant amount of antimatter particles also exist in space and only interact with themselves. But when matter and antimatter meet, it is a catastrophic disaster. Just as matter-antimatter pairs are created with perfect symmetry in fundamental interactions, they also annihilate each other in an equally symmetrical manner. When a particle of matter meets its antimatter counterpart, its kindred spirit, both vanish together in a blaze of fiery radiance. For example, a collision between a regular planet and an antimatter planet would not resemble a typical impact. They will annihilate each other down to the smallest atomic particles and release an immensely powerful, terrifyingly strong gamma-ray explosion. All types of particles, when combined, transform into energy, typically in the form of high-energy gamma radiation. The complexity of force interactions. We cannot observe any signs indicating that a large amount of antimatter particles exist freely in the universe. For we cannot see the inevitable consequences of destruction when ordinary particles collide. The universe is filled with matter, and between them, constant interactions are always taking place. High-energy particles hurtle across distances spanning several light-years. Material jets erupt from the galaxy, while new components surge inward where stars collide. In the universe, forms of matter are constantly and endlessly blending into one another. And if there were a quantity of antimatter particles, the universe would become far more intense than it is now. Therefore, the question arises: if antiparticles no longer exist here, then where have they gone? Where have they all gone? One hypothesis suggests that our universe was formed this way from the very beginning, with an extremely large number of matter particles and almost no antimatter particles. That is certainly an excuse, not an explanation. That is merely a folk saying, considered self-evident rather than a scientifically persuasive argument. Therefore, instead of continuing to discuss in this direction, let's shift to a different perspective, with more effective approaches to solve the problem. Perhaps something in the early universe created the imbalance between matter and antimatter. That is not a crazy idea. The first days of the universe were a period of chaos, marked by a series of extremely violent physical events. And those miraculous physical interactions, fortunately, have so far remained only as memories of the universe. Therefore, something must have happened. The early universe once evolved in perfect harmony, as particles of matter and their antimatter counterparts coexisted in a state of balanced and symmetrical equilibrium. And then, a shift, an imbalance, and a strange process that created more matter than antimatter. Although the majority of particle and antiparticle pairs will annihilate each other, a portion of ordinary matter will still be preserved. The remaining amount of matter was not substantial, only about 1 part in a billion, just enough to form the foundation for the stars and galaxies we observe today. The weak interaction force is one of the 4 fundamental forces of nature. Although its range is extremely short, limited to the size of an atomic nucleus, it plays an incredibly important role. This force is responsible for the radioactive decay of particles and is the foundation for the nuclear fusion reactions that allow the sun to shine. Actually, it takes an extremely special set of conditions to cause this kind of imbalance. Our universe operates according to principles that govern how particles and forces interact and behave with one another. It is these very principles that lay the foundation for all the wondrous interactions, contributing to the richness of everyday life. But sometimes, certain rules also need to be broken, just as the early universe itself once did. Ultimately, these very principles also confirm that particles of matter and antimatter inherently cannot coexist at a single point of origin. Any interacting force or process that ultimately leads to the triumph of matter is truly very strange. This process must begin by generating not only an excess of ordinary matter particles, but also an excess of anti-electrical particles to neutralize them. On the other hand, because the total electric charge of the entire system is conserved throughout the process, the material love path will be perfectly balanced with that of its twin antimatter particles. Furthermore, this process must occur during a period of intense upheaval, when the universe was rapidly transforming from one state to another. Only at that moment did physics permit the laws to be broken. Otherwise, a stable universe would be forced to end in a state of equilibrium between interacting forces at all costs. What in the laws of physics caused antimatter to disappear from the universe? It might be real. Currently, there are many hypotheses and proposals regarding rare forms of matter interaction, including weak nuclear interaction. We still only have a vague understanding of those interactions, particularly how they manifested in the universe's early period. However, even our best estimates of the dominant amount of matter are still too low, insufficient to explain the current state of the universe. In summary, the question of where all the antimatter in the universe has gone remains an open, compelling, and challenging problem for the scientific community. Although it was known that the Big Bang should have created equal amounts of matter and antimatter. However, observations indicate that only a very small amount of antimatter remains in the universe today. To explain this imbalance, various hypotheses have been proposed. For example, the possibility of a slight asymmetry in the interaction or decay between matter and antimatter. The origin of the asymmetry between matter and antimatter will forever remain a crucial and particularly captivating topic in the field of physics. A problem that has taken our current knowledge and understanding of the universe back to its earliest infancy. You could say this is a genuinely serious problem.